Alright, moving on to the exponentials and logs part. You should hopefully remember a lot of this from Algebra 2 and or pre-calculus, but these are typically fairly easy, and we'll end up focusing more on this for Calculus AP in the second semester. For Calculus BC, it's towards the end of the first. Anyway, so let's go for it. First one, you have e to the 2x minus 3 equals 75. Actually, before we get into these, let's review. I have some notes from what your previous classes should have covered. Let's see. Okay, yeah, pretty much gets it all. So you have the logarithmic form of an equation and then the exponential form of an equation, and you could always switch back and forth between the two. So you have a log base b of a is equal to x. If you wanted to switch it from log form to exponential form, you would take base b to the x power equals a. There's always kind of this circular motion to it. B to the x equals a. Or if you wanted to start from exponential and then switch it into log form, you would have log base b of a is equal to x. Logs are equal to the exponent, right? Logs are exponents. Kind of how my Algebra 2 teacher always said it. So either way you want to switch from one form of the equation to the other, it's always this kind of circular rotation aspect to it, and it kind of helps me remember. If you start with log and you want to switch it to exponential, b to the x power equals a. And if you start with an exponential and want to switch it to a log base b of a is equal to x. You can switch from either to the other, right? Pretty easy. Some common facts. Log base e. E is called the common base. Oh, sorry, not the common base. E is the natural base. So log base e of x, you really never are going to see it written like this. Log base e is the same thing as ln of x, right? E is the natural base. So we'll call log base e the natural log. That one comes up quite a bit. 10 is the common base, and log base 10 is called the common log. And if you ever don't see the base indicated, then it's assumed that you're working with the log base 10. So log base e is ln, which we work with quite a lot. Log base 10, which is the common log, or just log, we also going to work with quite a lot. And we like those mostly because the calculator can deal with them really quickly. Your calculator can do the other bases, you just kind of have to dig through the menus or know how to change the base. But log base e, natural log base 10, log, common log, most common. Remember, e is a constant, just like pi, except e is about 2.7. Ln of e is 1. And that's true because e to the first power equals e. Ln of 1 is equal to 0. That's because e, remember that's log base e, e to the 0 power equals 1. Alright, so two facts that you really need to know. Ln of e is 1. Those are inverses of each other, so they reduce, kind of like how multiplication and division would reduce to a 1. Ln of e is equal to 1. Ln of 1 is equal to 0. Alright, look at the two graphs. Here in red, you see the natural log graph, which has a vertical asymptote on the y-axis, right? You can never have a 0 inside of a log, nor anything negative. And then the x-intercept for the natural log graph is 0. It's 1. So right here at 1, that is where the natural log graph crosses the x-axis. And then you have the graph of the inverse. Remember, here's the line y equals x, the exponential function and the natural log, those are inverses. So they're reflections over that line y equals x. Here, if you have the vertical asymptote at 0 for the log, your corresponding inverse is going to have a horizontal asymptote at 0. If you had an x-intercept for the log, your exponential is going to have a y-intercept of 1, right? E to the 0 power equals 1, and so on and so forth. Okay, and then you have some log properties down here at the bottom. These are expanding and contracting logs. If you have multiple logs and they're being added, now it's important, you need the bases to be the same. If this was a log base 7 and that was a log base 8, you wouldn't be able to use this property. This is all assuming that the bases are the same. But if you have a log base x of a plus log base x b, right, same base, it doesn't matter what it is. But if you have addition between the two logs, what you can do is combine them. Of course, you keep the same log, right? If you had log base x and a log base x, you have that exact same log base in the condensed answer. But what you would do with these two arguments, if you have log of a plus log of b, you would take them and combine them, and then inside of this condensed log, you would have a times b. So when you have addition between the two logs, you could combine it, and then you would have multiplication within. Or vice versa, if you started with something like this and you wanted to split it up, you could. You could expand it. Multiplication inside splits up into addition between the two logs. Kind of similarly, you have subtraction between the two logs. That's going to go ahead and condense, but instead of multiplication, you're going to have division. Now, the log that was positive, right? You had the positive log base x of a, then minus the log base x of b, right? The one that's negative, right? See how the negative is in front of the log with the b inside of it? Since the negative is attached to the b log, that's why the b term goes to the bottom. We'll talk about that in just a second. But addition between the logs combines into multiplication inside, or vice versa. Multiplication inside splits up into addition between the logs. Subtraction between the logs condenses into division inside. The one that was positive goes to the top. The one that was negative goes to the bottom. Or vice versa. If you had division, you could split it up into subtraction. And then we also have this coefficient exponent rule. If you have a coefficient out in front of the log, what you could do is take that and then stick it as an exponent. So you have c, some constant, log base x of a. What you could do is take that constant out in the front and then stick it as an exponent of the argument. So you could have log base x of a to the c power. And of course, that property also works vice versa. If you have this exponent inside, you could take this and move it to the front, and you could change it from this form into this form. Right? So hopefully that makes sense. If you want to think about the subtraction rule, it's really nothing new. Like, let's just say if you had a log base x of a, am I on the screen? Yep. You could rewrite that as plus negative log base x of b, right? You could rewrite subtraction into adding a negative, but then you could take this -1 coefficient and you could stick it as an exponent. So you could have log base x of a plus log base x of b to the -1st power. And then we know if we have addition in between the two logs, I could combine them. We would have the same base. Now I'd have a times addition between the logs combines into multiplication. And then if you have b to the -1st power using your exponent rules, that's the same thing as a over b, right? So really the division rule isn't new, it's just a combination of the other two rules. And then also thinking about the domain issues, like you can't ever have log base -7, right? It doesn't work. You can't ever have a negative number inside of a log. Same thing with 0. You can't have a 0 inside of a log. It just doesn't work, right? Think about it like this. You have your exponential function, and e is about 2.7. Could I ever take 2.7, e, which is a positive number? Is there any exponent that you could raise it to that will give you out 0? Right? Think about it. Well, 2, if I took 2 and I squared it, well, that would give you 4. If you took 2 and you cubed it, that would give you 8, right? So on and so forth. Any positive base, there's not going to be a possible exponent that you could use. If you take a positive number and raise it to the exponent, it's just never going to give you 0. And since there's no exponent that you could take e to any power and give you 0, that's why you can't have, let's see, so you'd have log base e, so you'd have e to the 0 power is equal to this. Or you'd have a log base e of 0. Since there's no exponent that makes that true, there's also no value that's going to make the log of 0 true, right? So it just doesn't make sense. And you could do the same thing with negatives. Could I ever take e, a positive number, raise it to any exponent, and end up getting out a negative value? Could I take 2.7? Is there some number that I could take 2.7 and raise it to that some number power and get out a negative result? No. And since there's no value that could potentially give you, if you take that power, that could potentially give you out a 0, and there's no value if you take e and raise it to that power. It gives you out a negative. Well, that's why you can't ever have the 0 inside of the log or the negative. So your domain restrictions for your logs, your natural logs, your log-based 10s, your log-based whatevers, you can have any positive number inside of the log, but you can never have a 0 inside of a log, and you can never have a negative. And the whole idea is, because you can't take this positive base, raise it to any power, and get out to 0, that's why you can't have the 0 inside. And then also, you can't take a positive base, raise it to any power, and get out a negative answer, right? It's just not possible. That's why you can't have a negative inside of a log. So that's kind of just a little bit of review. Hopefully that's okay. And then let's go ahead and use those to speed through these questions. I like logs and exponentials. Once you kind of get a hold of those rules, they're pretty quick. All right, so first one, it starts off in exponential form. First thing we're going to do is rewrite it as a log. So you could think about taking a log on both sides, or if you really want to just think about it as rewriting it as a log form of the equation. Here I could have, right, you'd have ln of e, or log base e. So I'd have ln, which is log base e, of 75. So log base e of 75, and that's going to be equal to your 2x minus 3. You're just rewriting it from exponential form into log form. If we want to think about as taking a log on both sides, well, the ln of the e would cancel, and then the ln of the 75, I just kind of switched the sides of the equation. But it doesn't matter. Taking a log or rewriting it as the log form, that's the same thing. Okay, 2 more steps. You're going to have to add the 3 and then divide by 2. So I have ln 75 plus 3. And then here I'm going to have x. I'm just going to write a 1/2 out in the front. I know it says use a calculator. I really prefer the exact solution, so I'm just going to leave it like this. If you wanted to, in your calculator, you could type it in, and you could get the really weird decimal, which is 3.659. But I would rather see the exact solution, right? It's more precise, more accurate. Now, be careful. Do not tell me ln of 78 in here, right? The ln of 75 is one term, and then the 3 is a completely different, not similar term, right? So you can't combine things that aren't the same type of a term. So please don't go combining stuff inside of the log. And if you wanted to keep like those extra parentheses there to help you see the difference, that's fine. But this is kind of how I would like the answer to look. Okay, the next one looks a little bit tricky because I've got that e to the 2x. Well, here we're just going to have to remember the fact that we have some exponent rules. If I have e to the 2x, which is 2 times x, I could rewrite that as e to the x squared. Because if you have a power to a power, right, what you would do in order to simplify this is you would take x times 2. So e to the 2x is the exact same thing as e to the x squared. And if we rewrite it as e to the x squared, we can see how this one is just like one where we did with the trig, where you have something to factor. If you have something that's quadratic, it's squared, then you have some other coefficient, and you have that same something as linear, and then you have a constant, you could factor this. Now, if you need to, you could rewrite that as x squared minus 3x minus 10, and then you could factor it in terms of x. I'm not going to. If you need to, you can. I'm not going to. But recognizing that e to the 2x, that's the same thing as e to the x squared, and then you have something squared minus 3, you have that same something, then you have the constant. This is an equation that we can factor. And this one is going to factor e to the x minus 5, e to the x plus 2. Okay, and then we would set each factor equal to 0. So I have e to the x equals 5, e to the x equals negative 2. Here, let's solve it for x. So here x would be ln of 5, and then here x would be ln of negative 2. But that's not possible, right? That one doesn't give you a valid solution. So that particular part gives you no solutions, but you do have the ln of 5 value from the e to the x minus 5 chunk. Again, if you're curious about the decimal, this one ends up being 1.609. And for AP Calculus, you would always want 3 decimal place accuracy. I like the exact solutions, but if you did use your calculator, you need to make sure that you're accurate to 3 decimals. Okay, so that one you had to factor. A little bit weird, but very doable. Let's look at the next one, which before you factor, you're going to have to do either one of 2 things. I think technically the better option is to factor out. All right, this one's weird because you have that e to the negative x. The better option, more mathematically precise, is to factor out an e to the negative x. And when you factor something out, what you're doing is division. So if you had an e to the x, and if you divide it by e to the negative x, you would have e to the 2x. And then here, if I had plus 12 e to the negative x, if I factored out, if I divided it by e to the negative x, that would just give you the plus 12. And then here, if I had negative 7, and if I divided it by e to the negative x, I'd have minus 7 e to the x. Here, let me show you a little bit of an explanation, because students usually have a little bit of difficulty there. So let's say if I had e to the x, and if I divided it by e to the negative x, right, taking this first term and factoring out this, well, negative exponent on the bottom. The negative exponent means do the reciprocal. So if you have a negative on the bottom, that would be the same thing as flipping it and then moving it to the top, right? So this negative means you really want to move that term to the top. And then you have your e to the x, e to the x. That's the same thing as your e to the x squared. And then here, so it was pretty easy. You had your 12e to the negative x. And then we were factoring out the e to the negative x. And then that's pretty easy. You can just see how it reduces very nicely. And then the other one, we had the negative 7. And then we were factoring out the e to the negative x. When you factor something out, what you're doing is division. Again, this negative exponent, that's the same thing as just changing it from the negative to the positive and then moving it to the top. So factoring out that weird exponent is kind of the more precise way of getting the answer, but it's okay. Anyways, you have e to the negative x. Here we're going to rewrite this as e to the 2x. I'm just going to move this linear term. Equals 0 still. Kind of drop that off. And then this now is just like the previous example where we can factor it. So you're going to need factors that multiply to positive 12, but then add to the negative 7. So I think that's going to be a minus 4, minus 3. Set each factor equal to 0. Okay, so here you'd have, if you rewrite it, you'd have like negative x equals ln of 0, which that one doesn't have any solutions. Am I still on the screen? I think so. Oh, that's nice. Okay. So even though you factored out this piece didn't end up being important because that piece doesn't give you any valid solutions. So technically you should factor it out because it's there and it's kind of important, but it doesn't end up really generating any solutions. So you really don't have to worry about it that much. But this one, you're going to end up getting that x could be ln of 4, and then this one, x could be ln of 3. So we did end up getting 2 answers. The part that we factored out, you don't really have to worry about too much because it doesn't generate any valid solutions. A different way of doing this, right? So factoring out the e to the negative x, students will sometimes struggle with it. Another way to think about it is you're like, okay, I've got this e to the negative x, which you really don't want to have. If you wanted to get rid of it, what you could do is take that whole equation, and then if you think about multiplying by e to the x. Of course, if you multiply the left side by e to the x, you would do the same thing to the right, but spoiler alert, 0 times anything is 0. Then you could take this, and then you could distribute e to the x times e to the x. That's your e to the 2x. E to the x times this. The e to the x and the e to the negative x would cancel, which would give you the plus 12. Then your e to the x times the negative 7. Right, and so here you would still get this same factorization. Right, this e to the 2x minus the 7 e to the x plus the 12, and so then that would factor e to the x minus 4, e to the x minus 3, and you still get the ln of 4, ln of 3. You're kind of missing that extra piece, but remember that extra piece didn't end up giving you any answers that you were concerned with anyways. So either one is fine. I don't really care. You can either take this equation and then factor out the e to the negative x, but then that doesn't end up giving you any solution, so it's like not the end of the world. If you do it this other way, which is, I think, conceptually a little bit easier, you could multiply the entire equation by e to the x, and then I think that's just usually a little bit simpler for students to get their brains around. Either way is fine, but you should, for this example, get 2 solutions. I'm not going to worry about the decimals. I like the exact solutions a little bit more. Okay, so that one was a little bit weird. Let's move on to the next one, which is easier. Here I have 18 over e to the x plus 3. What I'm going to do is take this whole chunk and multiply it over. Right? The goal is to get the x by itself. So I need to get this chunk over to the right. You don't want to solve for x while it's in a denominator, so we're trying to eventually get the x by itself in the numerator. So multiply that chunk over. I'm going to divide the 5 over, and then subtract the 3. And then, let's see, 3 would be the same thing as 15 fifths. So 18 minus 15 would be 3 fifths. Now, the next step, right, to get rid of this exponential, the next step would be to take a log on both sides, or to rewrite it as a log. Now, let's check and make sure that that's okay. Is it okay to have an ln, to have a 3 fifths inside of a log? Yes, that's not 0 and that's not negative, so that's fine. It's like square rooting. Like, you wouldn't square root an equation if you have a negative on one side, because you know it's going to give you an invalid answer. So kind of the same idea. If that would have been negative, you would be stuck, because you shouldn't natural log when you have a negative or a 0 on the other side. But here, since that's positive, you do end up getting a nice answer. ln of 3 fifths. It's an ugly decimal. You know what's interesting, too? Let me pull out the calculator. If you were to do ln of 3 fifths, right, a lot of students get a little bit confused because when they type that in, you end up getting a negative decimal, 0.511, right? And a lot of students are like, well, where in the heck does that negative come from? Like, I see the ln, which has just a positive out in front, and I see the 3 fifths, which is positive. Well, you have to think about that natural log graph. Remember, the natural log graph crosses the x-axis at 1. Is 3 fifths before 1, or is 3 fifths after 1? Because anything before 1, that graph is beneath the x-axis, and you would have a negative value. 1 is when, if you plugged it in, ln of 1 would give you 0. That's this point. Anything bigger than 1 would give you out a positive result. Well, 3 fifths would be before you get to 1, so then the corresponding point on that graph would be beneath the x-axis. So it's weird. You can have something like 3 fifths, or 1/7, or 17/18. You can have these weird fractions that are between 0 and 1. You can have them in the argument, but just know that when I have something between 0 and 1 here, that value is actually a negative value. It's kind of a little bit tricky to see. But if you think about the graph, just think, is it before 1? Has it crossed? Or is it after 1? Okay, so there's your exponential equations. Let's move on. We've got 4 log equations now. And what you would do is kind of just the opposite. If you start with the log, you would want to rewrite it as an exponential. So remember, that's the same thing as log base e. So I'd have e to the 5th power is equal to 3x minus 2. You can either think about it as taking an e on both sides, exponentiating, or you just think about switching it from the log form to the exponential form. But you have e to the 5th power equals that stuff on the inside. And then you have 2 more steps, e to the 5th plus 2, and then you would, 3x, and then you would just need to divide by 3. And if you wanted to write it as e to the 5th plus 2 over 3, that's fine. Like sometimes I'll write the 1/3 out in the front, sometimes I'll just leave it as the divided by 3. I think I generally kind of like having the 1/3 is, I don't know, makes it look like mildly nicer, but those things are equivalent. They're fine. Okay, remember, e is just like pi. It's just a number. So e to the 5th is also just some number. It's probably some weird ugly number, but it's just a number. So that's fine. Okay, next one, I have log. Remember, there's no base indicated, so that's base 10, the common log. So I have log of 4x plus 3 equals 2. I want to rewrite this, where you can exponentiate it with the base 10, or you just rewrite it as an exponential. I would take 10 to the 2nd power, and that would be equal to the stuff that was inside of the log, the argument. 10 squared is 100. And then this one ends up being really fast and really easy, right? Subtract the 3. And then divide by 4. The little 3 dots, it's the mathematical symbol for the word therefore. 97 equals 4x, therefore, divide by 4, x equals 97/4. Okay. The next one, here we're going to use the contraction property. I see I've got a log base 5 and a log base 5, and I've got addition between those logs. I also have a log 5 on the other side. What we're going to do is combine those two logs into one. Okay, and we know if I have addition between the two logs, what I would do with those two terms is multiply them. So we're combining the logs on the left. Let's FOIL it out. X squared, you'd have a minus 2 plus 3, so that's just a plus x minus 6. So I have log base 5 of x squared plus x minus 6 is equal to log base 5 of 14. Since you have a log base 5 of this stuff equals a log base 5 of this stuff, you have the same log applying to both sides. They're just going to cancel. So here we just end up having x squared plus x minus 6 is equal to 14, which it just looks like a quadratic equation. Can I factor right now? Hopefully you thought yourself, no. Before you try to factor this, you need to make sure that you have a 0 on the other side. So before I factor, I need to subtract this 14 over. Always got to get it equal to 0 before you factor. It's called the zero product property, right? You don't factor when you have a 14 on the other side. You factor when you have a 0. Anyways, this one's going to factor plus 5 minus 4. Remember, always check your factoring by just foiling it, multiplying it back together, and it had better match. I've done these notes many times, so I know that's right. Set each factor equal to 0, so I'm going to get x equals negative 5, and then x is going to be equal to 4. So it looks like we have two answers here, okay? But there's something you should always kind of be mindful of when you're working an exponential, and specifically when you're working a log equation. It's that sometimes you can get answers that look valid, but are called extraneous. They don't actually end up working. And how you check is you take these answers and you need to go plug them in back to the original equation. And if you hit an issue, like a negative inside of a log or a 0 inside of a log, well then that answer, even though it looks like it's going to work, actually does not. We call those extraneous, right? So let's check. If I take 4 and I plug it in for x everywhere in that original equation, do any problems come up? Again, let's check 4. Let's see, 4 plus 3 would be 7, and 7's fine to have inside of a log. Take the 4, plug it in here, 4 minus 2, okay, that's fine also, right? Plugging in the 4 doesn't create any issues, but let's check if I plug in the negative 5. Negative 5 plus 3 would be negative 2. So right away, if I actually use this value for x, I would get a negative inside of this log, and you'd have a negative 7 inside of this one, so that's a problem. So that negative 5 was actually extraneous. An extraneous solution. So it looked like it was going to work, but it didn't. The only one we really cared about was the solution that did work and didn't cause any problems. So just always check, right? Always check and make sure that the answers for these log equations aren't extraneous. They don't cause problems. Let's go back and check the first two. I purposely skipped it, wanting to talk about the extraneous solutions on G, but let's go back and let's check these two solutions, right? Here on the example F, if I had 97/4, if I were to plug that in, well, 4 times 97/4 would be 97. The 4 and the 4 would cancel. And then you have 97 plus 3. Okay, so that one works. And then if I were to take this example, this answer, which is kind of weird, and if I were to plug that in for x, let's see, the 3 would cancel. And then you'd have the x, the e to the 5th plus 2. The 2 and the 2 would cancel, so you just end up having an e to the 5th inside. So that's fine, right? But you want to make sure that when you have these answers, when you plug them in, no zeros come up inside of the logs and no negatives come up inside of the logs, right? That's checking for extraneous solutions, which you need to do because sometimes you get answers that mathematically look like they're going to work, but then they actually cause problems when you try to plug them in. Okay, last one, and then we get to the bare example, right? So here we go. Log base 4 of 2x plus 1 minus log base 4 of x minus 2 is equal to 1. I can combine these two logs. I'll have a log base 4. When I combine them, since it was subtraction, it's going to combine into division. This was the term that was positive, so 2x plus 1 would go to the top, and then an x minus 2 would go to the bottom. Now, you can't just cancel this log base 4 because you don't have the same log on the other side, right? Here, you're just going to have to take this log equation and rewrite it as an exponential. So we'll do 4 to the first power equals all that stuff. And then we just got to solve this equation for x. So 4 to the first power, that's just 4. Then we will take this, multiply it over, and then it's just a typical like algebra 1 type equation which you should be able to solve, right? So 4x minus 8 equals 2x plus 1. Let's go ahead and move the 2x over. And then add the 8 over. Am I still on the screen? Yep, okay. So it looks like x is going to end up being 9 over 2 or 4.5. Either one is fine. Then let's check it to see if it's extraneous. It's usually not. Like if you only got the one answer, it's usually not going to be extraneous. It's when you have multiple, that's when one or both of them may not work. But I mean, it would be possible for your one solution to not work, and then overall you're just like, oh, no solutions. But generally, if you only have one answer, it's probably going to work. At least the way the AP exam writes their questions. All right, let's check it. If I plug in 4.5, 2 times 4.5 plus 1, let's see. 2 times 4.5 would be 9, 9 plus 1 would be 10, okay, so that's fine. And then if I took 4.5 minus 2, that would also be fine, right? That value for x would not give you an issue when you go through to plug it in. All right, so last one, here we go. We've got the word problem with bears. The population P of bears in a national park after 2 years is modeled by this function. Part A, how many bears were there after 2 years? So that just means when time equals 2, what is the p-value? What is the population going to end up being? That's easy. That just means take that function and then plug in 2. So to have 160 over 1 plus 7e to the negative 0.32. And you could type that in on your home screen, or you can use the calculator. I'm going to go ahead and use the calculator because I want to show you a couple things. So turn on this calculator. I'm going to go graph this sucker. Oops, not second. I'm going to go to y equals. So I'm going to go to 160 divided by, make sure you put a parentheses, because if you start typing, you're going to divide by 1, and then separately you're going to add this stuff. You want to divide it, and you want that whole denominator in the parentheses. Let's see, so we've got second e to negative 0.3 x. Instead of t's, your calculator is just always going to use x. So I've got it graphed. That's great. You can look at the graph. It may look a little bit weird now. Right? You may not really see what you want to see at first. You may have to fiddle with the window, but that's okay. We don't really need the graph right now. But anyways, how I want to evaluate this? Well, we know we could go to the table, and I could go ahead and look Well, when x equals 2, looks like I'd have 33 bears, right? So getting the value from the table is one way of doing it. But another way of doing it is to actually evaluate it from the home screen. And I want to show you this in case you've never seen it before. So you could snag the value from the table, that's fine. But if you wanted, right, you have some function stored in y1. If you just wanted to evaluate it, you don't have to go to the table. You could just evaluate it from your home screen. And here's how you do that, right? Remember, that graph, that function is stored in y1. So let's evaluate it. Let's plug in 2. So I'd come over here and I hit the vars button, stands for variables. Hit vars. Then you need to scroll over to the right because we want the y variables. So I scroll over to the right. And then this is just going to be which mode is my calculator in. For us in Calculus A, B, we are always going to be in function mode. We don't really ever fuss with polar mode, unless you're in Calculus BC. Then we'll do that a little bit at the end of the year. Again, we don't mess with the parametrics until Calculus BC. So for right now, we're pretty much always going to be in function mode. And then here is just like a little mailbox. You just, wherever you have your equation stored, you would just need to snag it. Like if you had it typed into Y5 for whatever reason, you would scroll down and you'd hit Y5. But I have it stored into Y1. So I'm just going to click Enter. And then it's kind of got the function there for me. And then I need to open a parenthesis, type into close parenthesis. I'm snagging my function. I'm snagging that little algorithm. And I'm telling it to evaluate. Just like when you have f of x, right? That's the x inside the parentheses. That tells you what value to evaluate the function at. And then that's going to end up giving you the same value, right? That the table did. 33.046. That's the same thing we have here. We'll do that one more time just so you can follow, right? So you can get the value from the table, or you can do vars, scroll to the right, y vars. We're in function mode. And then wherever you have it stored, which for me is Y1, and then you got to remember to evaluate it. If you wanted to find the population after 3 years, you would type in 3. Or after 15 years, you could type in 15. But we didn't want that. We just wanted it after 2 years. So then you can evaluate that function from the home screen. And then we'd end up getting 33 bears. So therefore, 33 bears. For population models, you were generally always going to round down. Even if that was like a 0.746, 0.746, that would be like a bear missing an arm or something. That doesn't really count. That would be a dead bear very soon, right? So generally for population models, you would just always round down to the nearest whole number unless the question tells you otherwise. But here it was nice. Since it was below a 0.5, you would round down anyways. Alright, so anyways, last one. After how many years will there be 50 bears in the park? So this is not asking you to take the function and then plug in 50, right? That's how many bears are there after 50 years. This is saying, what's the t-value going to be when the population is 50? You know it's going to have to be more than 2 because the population is only 33 at 2 years. So really what we'd want to do is take this equation and I would set it equal to 50. Now, we could solve this algebraically, but since we have a calculator, we're just going to go ahead and use the calculator, right? If you're curious about the steps for solving it algebraically, you can go look at my notes key on my website, and it shows you all the steps. Or I guess you don't have to look. You could just pause this video, and then you could look at the steps. We'll focus more about solving these algebraically later on when we get to the unit in calculus dealing with exponential equations. But for now, this is just a review. We'll find how to get the solution using the calculator. And what I would want to do is graph one of these equations in y1, which I already have done. And I'm going to graph the other one in y2. Now 50 is a constant. It's going to be a horizontal line. And then I'm just going to graph with my GDC, Graphing Data Calculator. And I'm going to find the intersection. Now, an important thing to do if you're working in my class or if you're working on the AP exam, when you're going to use a calculator, which it's expected for you to do at certain points, what you need to do is write on your page what you're doing. You can't just have this written and then have the answer magically appear from thin air, right? You need to tell me, here's what I graphed in Y1, here's what I graphed in Y2, and then you need to tell me what you did with the calculator. So don't just have the numbers appear. You need to write a little note, so that way you're proving that you understand what you're doing, but you're just using the calculator to do it. Alright, so I've got the function typed in. Now I need 50. Now I know if I graph it, I'm not going to see it, because the typical window only goes up to 10. So I'm going to have to change the scale. I'm not going to need negative time, and I'm really not going to need anything below, because there can't be a negative population of bears. So I'm going to go change this window. I'm not going to need X-min. X-max, I'm just going to leave that at 10, right? Who knows? That's going to change the right side of the graph. We'll count by ones. I'm not going to need 0 bears, or I'm not going to need negative bears. Let's go up to 100, right? And let's count by tens. So here I'm changing it. Now it's going to be 0 to 10, counting by ones. And then it's going to be 0 to 0 to 100, counting by tens. So there's my population model, the Y1 function graphing. There's the horizontal line, population being 50, and then I would want to just find this intersection point, right? And how you do that is you hit, you need to calculate, so I'm going to hit second, trace, or calculate. If you wanted an x-intercept, you would do a 0. If I wanted a min or max, this is also if you wanted the population at 2, you could find the value at 2, but that's I think harder than just using the table or evaluating it on the home screen. But if you wanted an x-intercept, a minimum or maximum, you could find all those things. We're actually going to want the intersection point. First curve, you just need to make sure that your little cursor is somewhere on the first curve, which it should generally start on the Y1. So click enter. Second curve, you need to make sure that your cursor switches, and now you're somewhere on the second graph, which it should automatically move to Y2. And then the guess doesn't really matter, since these solutions, or since this graph only has one intersection, the guess doesn't make any difference. But if your graphs cross multiple times, you'd want to scroll over and click closer to the intersection point that you want. So here I'm just going to scroll over, and we can see that that intersection point is 3.858. And then don't forget your units. The units for this time value would be in years. So hopefully all that stuff with the exponentials and logs, hopefully it wasn't all new. It should be a lot of review. Maybe some things are a little bit of a refresher, like you forgot how to do. But if you have any questions, please feel free to email me. Remember, always check the homework keys when you're working on the homework, because a lot of the times you can just use my step-by-step guide to help yourself and to correct any issues pretty easily.